Today I am going to discuss thermal modeling of a machine. We know that whenever machine is under load condition, then its temperature increases because of losses across the system. Now its temperature keep on increasing till steady state temperature. The temperature at which heat developed by the machine is equal to the heat dissipated to the surroundings. The temperature is known as steady state temperature. In last lecture class, we have discussed about different issues in estimation of motor power rating. One of the issues earlier also I have discussed that accurate prediction of heat flow is almost impossible because heat dissipated through different parts of the machine is not constant because of the complex geometrical shapes and the use of heterogeneous materials. What is the solution of this problem? We know that conductivities of different materials do not differ by a large amount. So we can assume that complete machine is a homogeneous body. Based on that one, we will derive our expressions. Thermal modeling of a machine. Now a machine, when it is loaded, its temperature keep on increasing. When it is unloaded, then its temperature cools down. In this lecture class, we will discuss about the thermal modeling of machine during loaded condition only. Some assumptions we have taken, that is, let the machine is assumed to be a homogeneous body and the cooling medium has following parameters at time t. P1 heat developed in joule per second. P2 heat dissipated to the cooling medium in joule per second. W weight of the active parts of the machine in kg. H specific heat of consumption joule per kg per degree centigrade. A cooling surface area in meter square. D specific heat of dissipation joule per second per meter square per degree centigrade. Theta mean temperature rise in degree centigrade. Let's assume that in time dt there is increase in temperature of the machine d theta. Now we know that if a machine is operated or a load is connected across the machine, then temperature of the machine will increase. We can write this expression that heat absorbed in the machine is equal to heat developed inside the machine minus heat dissipated to the surroundings. Now heat absorbed in the machine. Heat absorbed in the machine is equal to W into H into d theta. H is specific heat of consumption. W weight of the active parts of the machine in kg. And d theta is the rise in temperature in time dt. So W into H into d theta is the heat absorbed in the machine. Heat developed inside the machine is equal to P1 into dt. Because P1 is heat developed in joule per second. P2 into dt. P2 is equal to heat dissipated to the surroundings in joule per second. So we have got this expression, equation number 1. Now we can also write P2 is equal to theta into d into A. D is a specific heat of dissipation and the unit of specific heat of dissipation is joule per second per meter square per degree centigrade. So if the specific heat of dissipation is multiplied with area and temperature, then it will give heat dissipation to the surrounding in joule per second, and when it is multiplied by dt, it will give you total heat dissipation to the surrounding. So number 1 can be now modified. W into H d theta dt is equal to P1 minus dA theta. Again, by rearranging the equation number 3, C d theta dt is equal to P1 minus P2 is equal to P1 minus d theta. Here C is equal to thermal capacity of the machine in watts per degree centigrade and D is the heat dissipation constant in watt per degree centigrade. Equation number 4 is written as C d theta dt is equal to P1 minus d theta. This is just first order differential equation. Solving this differential equation, we will get the value of theta. So theta is equal to P1 by d 1 minus e to the power minus t d by c plus theta 1 e to the power minus t d by c, where theta 1 is the initial temperature of the machine. That means when t is equal to 0, temperature of the machine is theta 1. Now at t is equal to infinity, theta is equal to P1 by d. That means if the load is connected to the machine for infinite duration, then a constant temperature or steady state temperature of the machine will reach. That is also known as equilibrium state of the machine. In that state, heat developed by the machine is equal to heat dissipated to the surroundings. Now, C by D is equal to WH by dA, and the unit of this is in second. C by D unit is second, and that is represented as tau and is also known as heating or thermal time constant of the machine. So the expression of temperature during load condition can be written as theta is equal to theta SS 1 minus e to the power minus t by tau plus theta 1 into e to the power minus t by tau. So this equation number 6 will give the temperature of the machine based on the operating or operation duration of the machine. If the machine is operated for some duration of time t, then it will give the temperature of the machine after that time. So equation number 6 is valid only for loading condition. So today we have discussed about the temperature of the machine during load condition. Based on that one, we can find how much or what is the steady state temperature of the machine. Accordingly, we will select insulating materials for the machine. In next class, we will discuss temperature of the machine during unloading conditions. That means when the load is removed, how much time it will take to achieve steady state or environment temperature.